equivalent circuit of a transformer. Yeah, equal. Okay. We need to transfer in this chapter because we want to analyze a single phase transformer. What we need to do is we need to transfer the hardware into a circuit. But it is quite complex, so we will transfer one step to one step, and then we call it as an equivalent circuit, which we make it as average, or we have set some assumption so that to make the circuit simple. Okay, so the process is we will study the exact equivalent circuit first, we call as a real transformer, and then we will approximate the equivalent circuit as a real transformer. So why we equivalent circuit? Why we need equivalent circuit or transformer is actually we need to analyze the practical circuit containing the transformer. We need to convert the entire circuit to an equivalent circuit of a single voltage level. Single voltage means, for example, if let's say I step up a transformer from 230 volt to 1000 volt, it is two voltages. But if it happened in this circuit, we cannot analyze it. We need to put into one voltage to make it one single voltage level so that for us to analyze it. And then we require to calculate the total internal impedance of an electrical power transformer moving from primary side or secondary side as per requirement. And then the reason also is impedance extends to the concept of resistance to AC circuit and possesses both magnitude and phases. So the major items to be considered in the construction of equivalent model, we have a model 1. We need to consider model 1, model 2, and model 3. One is so that to construct the equivalent model. Model 1, we need to come out couple loss. We need to consider the couple losses. We put the variable called RP and RS. And then the couple losses are the resistive heating losses in the primary and secondary winding of the transformer. Model 2, if you still remember the leakage flux XP XS, the fluxes, the leakage flux on the primary side, the leakage flux due to the secondary side, which escape the core and pass through only one of the transformer windings. Model 3, the excitation branch RC and XM, which is an eddy current. It contains the eddy current losses and hysteresis losses also the magnetizing current. So let's go through it. So model 1, copper losses RP and RS. This is the model of the real transformer. We have the resistive winding, inductive resistance of the winding, inductance of the winding. We have an excitation branch. This is excitation branch. We have a number of turns. This is all primary side. All primary side. Then we have a dot. This is so-called the dot convention, so important. Then we have a winding. And then secondary side. Then we have a resistance and the inductance of the secondary side. So we have a VP, we have a IP, we have a VS, we have a IS. So for the copper losses, RP and RS, RP is the resistance of the winding for the primary winding, resistance due to the secondary winding. So copper losses are resistive losses in the primary and secondary winding of the transformer core, can be modeled by RP, primary circuit, RS, secondary circuit. So this is RP, this is RS. Okay, just forget about the rest first. RP, RS. Same model. Now we want to model the leakage fluxes XP, XS. This is XP. This is XS. XP, XS. So from Faraday's law, EMF or leakage EMF due to the leakage of the primary winding is E equals to N d phi dt, right? E also equals to N d phi dt only. This is due to the leakage primary side, leakage to the primary side, leakage to the secondary side, leakage due to the secondary side. Since much of the leakage flux path is through air means there's no cutting to the winding. And since air has a constant reluctance much higher than the core reluctance, So actually the leakage flux due to the primary winding is directly proportional to the IP, and also leakage flux due to the secondary is directly proportional to the IS. Then we can put in a simple equation where we call as a flux leakage flux due to the primary is equals to P, or this is permeance, times NP times IP. Permeance is actually what you know. Permeance of the flux path. Permeance is a characteristic to describe how good the flux can go through somewhere. It is a ratio lah. 1 is a perfect no? Because if let's say permeance is 1 means all the NPIP that generated from the winding will become the fluxes. If 0.5 means only 50% of the NPIP will convert into flux. Okay, so permeance is a characteristic to describe how good the flux can flow through from one place to another place. So permeance will depend on the permeability lah. And then yeah, so we put in a simple equation, then we substitute into this one. It becomes like this. So I substitute into here, and then this is constant. I take out because I want to differentiate with T. So which one have T? Permeance don't have T. NP don't has variable T. IP, yes, it has variable P. So I need to put like this. Then I take out these two. Same as well. Permeance don't have a variable T, and S don't have variable T. IS has variable T. IS is actually like this. It is IS instantaneous with T. So I need to put like this, DIS dt. But NS squared times P. Okay, then I can factorize, become like this, where I make this become LP. NP squared P equals to LP. So E LPT equals to LP, this one, times DIP dt. Same as well for this one. Okay. Next, this is the model number 2, where we include the leakage flux XP and JXS. Next, I need to consider excitation branch. So the magnetizing current is a current proportional to the voltage applied to the core. If you still remember, magnetizing current is used to describe the flux path. Okay, if you still remember the flux path, the flux versus the MMF. It is like this. Then we have a magnetizing current here. Then we have an applied voltage here. If you still remember okay. Then it's a current proportional to the voltage applied to the core and lagging the applied voltage by 90 degrees. So it can be modeled by a reactant. This is due to a magnetizing current connected across a primary voltage. And then the core loss current, which is a hysteresis current and the eddy current, is a current proportional to the voltage applied to the core. You see, this one is proportional to voltage applied but in phase with the applied voltage. So it can be modeled by resistance connected to the primary voltage source. So one is in phase, one is a lagging. Okay, that's why we have two in the excitation branch. We have two things. One is RC, one is XM. RC is to cope with the IH and IE. XM is cope with the magnetizing current. So this is an accurate model of a transformer, but it is not a very useful one. It is not a very useful one. Why? Because it is not a single voltage level. You see, I have a VP, I have a VS. I cannot analyze. The circuit is not interconnected. It is isolated. So to analyze practical circuit containing transformer, it is normally necessary to convert the entire circuit to an equivalent circuit at a single voltage level. So the equivalent circuit must be referred either to its primary side or secondary side. Either we move everything to the primary, or either we move every parameter to the secondary. Okay, this is why we call single voltage level. So before we moving this one, for sure we need to come out the equivalent circuit, and this one is the exact equivalent circuit. And then exact equivalent circuit, actually we cannot analyze it so easily. So what we need to do is we try to simplify it. We try to simplify it. So let's have a look under these two figures. So the top one is actually we refer the secondary side to primary side. This one we refer the primary side to secondary side. So let's have a look. We call equivalent circuit of a real transformer Then, okay, from these two, once we refer from the secondary side to the primary side, or primary side to the secondary side, the parameters are different. You see these parameters are different. When we refer the secondary side, the parameter will be different. When refer the primary side, the parameter will be different. Okay, but the excitation branch of the model adds another node to the current being analyzed, make the circuit solution more complex than necessary. So it is even though we already transfer the secondary side to the primary side, or the primary side to the secondary side, in this situation or in this form, it is still a very complex for us to analyze it. So what we need to do is our solution. This is the solution. The excitation branch has a very small current compared to the load current. The current here will be very small. Okay. In fact, the excitation current is only about 2 to 3%. So what we need to do is the excitation branch is simply move to the front. So we can move to here, or we can move to here. Same as well, we can move to here, or we can move to here. Move to here means we can move to this one. Then we take off this one. For example only lah. So we can simply move to the front of the transformer, and the primary and secondary impedance are left in series with each other. So these impedances are just added, creating the approximate equivalent circuit. So that's why we have real exact equivalent circuit, then we will go to approximate equivalent circuit like this. Okay, so this is how we before we move it, actually we need to know how we create, how we refer it. Okay. Okay, now we talk about the transformer model that refer to its primary voltage. Okay, this is the one which is we don't want, because there are two voltage level. We want to put it into single voltage level. What we need to do is, for example, let's have a look on the red box first. So I have a RP, XP, RC, XM. I remain it. I just copy down. I copy all the parameter, include IP, VP, everything the same. This one, it will be everything the same. Then I refer the primary side. I refer the secondary side to the primary side, like this. So you see, from RS, XS, IS, VS, it becomes A square RS, A square XS, IS over A VS. This is how we refer. It becomes one circuit. Now this is two circuit, this is two circuit. This is one circuit. It is connected. This is not connected. So how we get it? Okay, let's have a look. As we know, let me take out the laser pointer first. As we know, VP over VS is A. IS over IP is A as well. VP over VS equals to A squared. P is stand for primary, S is stand for secondary. We want VS to primary side. We want to refer Vs to primary side, which is we call it as a VSP lah. V secondary refer to the primary side. So VSP is a VP lah. Vs will be retained is my A. So my VSP become AVS like this. So similar derivation for other parameters. I want to find my ISP, this one. I want to find my ISP, this one. So ISP as a primary side, IS is my secondary lah. So 1 over A, then my ISP become IS divided by IA lah. I move top. Then ZSP as well. ZS will be maintained, become A square. Then my ZXP is A square times ZS. So I break into two components, R and XP. So my R secondary resistance refer to the primary side, or it become my secondary resistance refer to the primary side, it become A square RS. Secondary reactant refer to the primary side, become A square XS. So this is how we refer lah. Next slide. Same as well. Just now I refer the primary, secondary to primary. Now I refer primary to secondary. So I remain secondary. So you can see VS, IS, RS, JXS all maintained. But I refer the primary to secondary side. So become VP divided by A, AIP, RP over A square, JXP over A square, RC over A square, JXM over A square. All the derivations are the same. I'll have a look on this. Just the difference is we have a RS and XMS. So RS is the R core, refer to the secondary side. XMS is the magnetizing reactant, refer to the secondary side. Okay. So now, just now we talked that we said that it is unuseful if let's say the nodes is maintained here, but we can move at it in front of this or here. Okay. Usually we move in front here. Okay, we move to here. This one, this branch, we move to here. Due to the small current on this portion. Okay, so it become it has two things. One is with the excitation branch, one without excitation branch. If I move this one, I can add up RP with A square RS, become my R equivalent. I can add up XP and A square XS, become X equivalent like this. So this add up become R equivalent. Let me take out my pen. So I add this one and this one. I have this one. Then I have this one. Then this maintain. Okay, I move maintain. I move to here. This one. Then I add up this one and this one. I get this one. Same as well. Same. Just that I don't have the magnetization branch. And this equation you need to remember. So we call it as an approximate equivalent circuit. This is approximate equivalent circuit that we can use to analyze because we only have one branch here and another branch here. Okay? Same. Just now is a secondary refer to the primary side. Now is a primary refer to the secondary side. Then I add up this one, become this one, which is this one. Then I add up this one, become this one. Then I have this one. So one is without excitation, one is with excitation, one is without excitation. Okay. Then we call as approximate equivalent circuit. Refer to the secondary side. Yeah. Next, we will talk about the open and short circuit test. Open circuit test. Open circuit test we call as no load lah. No load means no connection lah, on the terminal. Or the resistance is very high. Short circuit means we short the terminal lah. We call impedance test. For the transformer, we only have these two tests. Very important one. Why we need these two tests is we need to study the characteristic of the transformer. So these two tests are performed on the transformer to determine the approximate value of the inductances and the resistance. Just now we have approximate value, right? We have approximate equivalent circuit. This one. These two. This one. This one. This one. This one. Right? The problem is how to study it. These two. We need to have these two tests. And then the power required for these two open test and short circuit test on transformer is equal to the power loss occurring in the transformer. Okay? Next, the main purpose is, next we talk about the open circuit test first. The main purpose is to determine the no load test. How the transformer, what is the losses when there's no load connected to the transformer. One winding of the transformer, usually high voltage, is kept open, and then another one is connected to supply a normal voltage and the frequency. Then we need a wattmeter, voltmeter, ammeter are connected to the low voltage winding. For example, like this. Okay, high voltage no connection, low voltage with connection. But we need to connect wattmeter, ammeter, and voltmeter. So one transformer winding is open circuit, and the other winding is connected in a full rated line voltage. Full line voltage is applied to one side of the transformer, this one, and then input voltage, input current, input power to transformer are measured. The watt, ampere, volt are measured. The measurement in the open circuit test is normally done on the low voltage side. This is low voltage side. LV is a low voltage side of the transformer, since lower voltages are easier to work with. So for example, this is 2400 volt, 2400. This is 24 volt. Which one is easier to apply? For sure it's 24 volt compared than 2400 volt, right? So it is possible to determine the power factor of the input current and both the magnitude and the angle of excitation impedance. Since the high voltage side is open, the input current IOC is equal to the excitation current through the shunt excitation branch. Because this current is very small, about 2 to 6% of the rated current, the voltage drop across the low voltage winding and the winding copper losses are neglected. I put it into a simpler way, this one. So assume that this is a low voltage, this is high voltage, our equivalent. Okay, so first I open circuit the high voltage side. Second, I connect the power supply until V rated. Just now I give you an example. This is a 2400 volt. This is 24 volt, for example. Lower voltage is easier to work with the lower side because it's easily for us to input 24 volt. Remember, open circuit test, it must be injected with a rated voltage, which means if let's say the transformer is 24 volt to 2400 volt, it must be 24 volt. If this is 12 volt to 2400 volt, I must inject 12 volt. So for example, this is 12 volt. So the second step, we inject 24 volt. 3. Since the voltage is low, since it is open circuit, IS will be 0. So 4. The current flow in the primary side will be very small. Okay, because there's no current flow inside here, right? So the current flow will be very small. Then we will omit this one. So we only have the excitation branch. Compare, because of the 4, right? The fifth one, because the RP and XP are too small. This one and too small as compared with the RC and XM. So significant voltage will drop across the excitation branch. If you still remember, if there's a current flowing through this circuit and this was so small, the voltage will taken by here. That's why we omit this one. Then so all the current will flow into the excitation branch. So the OC, open circuit test, we call OC, will give us RC and XM, these two. Then we need to put into the equation. So the conductance of the core loss resistance is given by 1 over Rc. The susceptance of the magnetizing inductor Bm equals to 1 over Xm. So the total excitation admittance is YEM equals to GC minus JBM. If you come across with Z, this Z is actually Z is actually 1 over YE. Okay, but here we start from this one to get Y first. Later we'll know you know why. Okay. Sorry, I would like to the explanation start from here is actually for us to easily to do the calculation later on for and better understanding. Okay, then I input this to here, I input this to here, and then this is the final equation for YE. Then the magnitude. Remember, we have two things. One is magnitude, one is the phase. So the magnitude is I over V lah. We know Z equals to V over I, right? This is the same. This is I over V. The magnitude lah. So the angle of the excitation, angle is power factor which is a cos theta. Is the loss, is the wattmeter that we read, and then the voltage and the current that we apply in the secondary side or low voltage side. Then the power factor is like this. So remember, because transformer is always lagging. That's why the magnetizing current is always lagging by 90 degrees. So remember, we need to put a negative value. Okay. Once we calculate this theta this theta, then we need to inject a negative value. And finally, this is the final one. We need to find it, where IOC divided by VOC in RMS value, angle, negative, theta. So just to make it a brief summary, open circuit test parameter. Okay, actually they will give us the POC, VRMS, and RMS. The problem is we need to find out the RC and XM. So given that POC, V, and I can find my theta. I also can find my magnitude, I over V. Then I put into the final equation, Y equals to I divided by V with the angle of a negative theta, and equivalent to this one. So once I have this value, this value, this value, I can get in the rectangular form. And then I compare GC with this one, BM with this one, and then I can get my RC and XM. Okay? Next, we'll talk about short circuit test. So method to determine its is equivalent impedance, leakage reactant, and the resistance refer to the winding placement. And the copper loss and a full load used to calculate the efficiency of the transformer, and also the total voltage drop. That's why we call as an impedance test. We want to determine these three things. So I think I will skip this one. You can have a look because I put explain it here. Okay, first of all, we as well put an equivalent circuit. Usually we will short circuit on the low voltage side. Okay, we will short circuit on the low voltage side. Second, we will connect the variable low voltage source. Okay, for example, low voltage source. Let me write something. Low voltage source 24 volt. This is a 2400 volt. Okay. The experiment here is we need to put a small voltage, not rated voltage, small voltage. Not V rate, V rate no. Not V rate. Small voltage, okay? Small voltage. 24 volt, we will short circuit it. Then second, we'll connect to the variable low voltage until I rate. Yes, just now is V rate. Now I need I rate. Okay, now I need I rate. And then lower current are easier to work with the high voltage side. Okay. And then the third one, the current will flow in the secondary side because of short circuit. The current also will flow in the primary side. And then since the input voltage is so low, and then negligible current will flow through the excitation branch. We don't need to excite it actually. Okay, we assume there's no current will flow through it. So all the current will flow through this one. So all the voltage drop in R equivalent and X equivalent. So the short circuit test will give us R equivalent and X equivalent. This is actually well explained in this one, but I did not read it out. Okay, since the input voltage is so low during the short circuit test, negligible current flow through the excitation branch. Then, okay, just now we want to find Y. Now we want to find jack, but we remember we need to put it as a jack short circuit. As here it put as a jack secondary lah. Is it jack SE short circuit? Maybe series impedance refer to the primary side. So Z is a V over I, power factor the same, P short circuit divided by V times I. So next we'll put into a polar form. You see just now YE also is a polar form like this. YE in a polar form like this. Okay. ZE also also put in a polar form. Then we equate into rectangular form. Then we get our R equivalent, X equivalent, either in the primary side, okay, either in the secondary side. So note that the open circuit test is usually performed on the low voltage side. Then RC and XM usually found refer to the low voltage side of the transformer. And the short circuit test is usually performed on the high voltage side. R equivalent and X equivalent usually found refer to the high voltage side. Now a bit confused. Later we'll go to the sample question, then you will understand. All the elements must refer to the same side, either high or low voltage side, to create the final equivalent circuit. That's why the final equivalent circuit will be in the same voltage level. A brief summary: short circuit test. PSC, power will be given, V will be given, R will be given. We just want to find this thing. Okay? In order to find the theta, remember theta is positive. Just now the Y theta is negative because inductance. So jack theta is positive, V over I is given, theta will find from here, then I can find my R equivalent and X equivalent. Okay.